Hi. So I thought maybe I do the course maybe like the first half, and then we can discuss the exam, which you already started doing, right? So good. So this last little subject is just really a view to the outside. In fact, next semester I'll do a course on Hilbert schemes of points, so it will be just a smooth continuation of what I have been doing, what I started doing now. So this is a huge subject, and I think it's very pleasant because it's in a certain sense more elementary than many of the technical things that are involved in the first half of the course, but on the other hand, it's a very active area of research, so there's still millions of things unknown, even about Hilbert schemes of points on the plane. So I will say a few things, but there'll be one thing that you are required to know, not everything. So I'll point out what you need to know for the exam. So the rest is sort of this story that, as I said, continues. Yes, so what I wanted to explain today is just how to localize on Hilbert schemes to, I'll erase this maybe, and what you need to know for that. So I'll just set up the basic objects. So the purpose today is to localize on Hilbert schemes, but first I describe in a bit more detail of just what the most basic things that we need. And this is the following. So what I was saying is that for every n, you have the Hilbert scheme of points on the plane, and these were just the ideals in R, where R was this ring, right? So all ideals in this ring R, and then the basic setup, the basic point of view is that we are thinking of this a little bit like, so I just recall the basic theorem that we have, that we can think of this as a smooth Grassmannian. I mean, amazingly, this looks like a smooth Grassmannian. So we have this thing. So there is this is some space now. We can, this is this loose notation of writing the trivial bundle with this ring as the fiber, and then there is, just like for the Grassmannian, we look at so this is like what was Cn for the Grassmannian, and then we look for the corresponding subspace parameterized by, so I point here as an ideal, and I just do this tautological sequence. So you have the same tautological sequence, and here I'll just put A for algebra. So this is now a sequence of R modules. So the theorem actually says that, so Hilb n is smooth dimension to n, and this is the tautological sequence is a sequence of R modules. So this sequence is a sequence of R modules, and the dimension of A, the usual, not R dimension, but just the usual dimension as a complex dimension, say, of A is equal to n. And so you did some problems in the homework for the simplest case when n equals 2. So again, the idea is, the basic setup is that I would like to think of this as a Grassmannian and do same sort of calculations like Grassmannian calculations that we did calculate Chern classes. Now so this bundle is, of course, these two are infinite dimensional, but this one is finite dimensional. So we can, in principle, calculate the Chern numbers of this bundle. And this will have some enumerative significance. And as I said, this is a very active area of research, but that I will not explain that. I will just, but I will explain how to do the calculation. So that's our only purpose for now. And okay, so maybe just to have a picture of what's going on, since now you've done the exercise for n equals 2, so maybe this will be easier to understand. So first of all, we can, for each I, so this is what we know, for each I, we can define the support of this thing. So this is the first thing, the support. We can define the support of I, which will be a finite set in A2. And this finite set is simply the points in A2 no. So this will be just all the points where the functions vanish. So all the points in A2 such that okay, so this is where the support is. So the support of the ideal, of course, could be n different points, but could also just be 1 point. So we don't know precisely how many. It's the number of points in the support is from 1 to n. So you saw some examples for n equals 2 when the support is 1 point, but it could also be support is 2 points. Okay. Now, once you have this support, you can decompose. So now you can decompose the ideal according to this support. So this I will not explain. This is some technical thing about localization. You basically have to invert some function and do some calculation. But anyway, a proposition which is that for each point in the support of I, you can define an IP, an ideal IP. So sorry, maybe I'll write it here, an ideal IP. So this is also another ideal, but such that now, the support of IP is just at the point P. So it's just supported there. And this is the part of the ideal which is supported at that point. So in fact, the ideal will be just the product of all the ideals in its support. Of I. Okay, so what this simply means is that suppose you have the support, suppose n equals 4, and your support is, the ideal is 3 points. You have 2 usual points, and you have a thicker point here. Whereas, well, I'll explain, I'll just introduce that thing in a second. So then you can represent the whole ideal that you're looking for as just the ideal of functions vanishing at this point, an ideal of function vanishing at this point, an ideal, a certain ideal supported here whose codimension is now 2. So this is what you were doing here. But the idea is that you can separate these things. So this corresponds to our intuition that we are just compactifying the general case when you just have n different points. Then, of course, there's n different points. The ideals are completely independent. Then, if you have n different points, then each of these ideals is simply the ideal of codimension 1, where the functions vanish at that point. Right? Okay. So then we can define the multiplicity. We can define the multiplicity. This is sort of just to give you a picture of what the thing looks like. I'll explain in a second. So we can define the multiplicity of I at P, which is just the codimension of IP. And of course, we have that the sum of the multiplicities of P at I, which is just equal to the sum of the codimensions of IP. So here the sum is taken for all points in the plane, if you like, is equal to n. So what you see is that you get some sort of a partition of n. In this case, it's 1, 1, and 2. And then in each of them, you can sort of look at separately. Looking for chalk. Okay. So in a certain sense, what this is intended to give you the picture, following picture. And it's really sufficient to understand, in fact, what's called the punctual Hilbert scheme. So the complexity, in a sense, the complexity of this the Hilbert scheme of endpoints reduces to understanding, in a certain sense, the situation when all the points are together. Zero, which is just those ideals, so this is a subset of Hilbert n, whose support is just the origin. So when it's supported just by one point. And so you saw this situation for the 2 points. So then when the thing was supported at the origin, this was P1. So you saw that Hilbert 2, 0 is just P1. Okay. So why do I say that the complexity reduces to this? Because obviously then you can write you can sort of motivically, if you just write as a disjoint union, you can, what I mean by this complexity reduces is that we can write Hilbert n as a disjoint union so you just look at Hilbert n equals, and then, well, I won't even write down precisely, but so you just look at some L1 plus LK equals n. So you write a partition of this number n. So this is this partition you see. You have, for example, 1, multiply 1, 1, and 2. And then for each k, now you choose P1, Pk, which are in the plane, the corresponding points. And then once you decided that, then you just have the product of Hilbert n. And now instead of 0, I'm just going to put there the Hilbert Li, and here I have Pi. Okay? So this is the picture I wanted to show you there, that you can represent any Hilbert scheme as just choosing some of n is choosing some k points. For each k points, you choose what this multiplicity is, and then the thing is represented as the product of the corresponding sort of local Hilbert schemes. Okay. Okay. So of course the biggest. So this gives you some sort of strata. The biggest strata is when you choose all of them to be 1. So then you just get Hilb. You choose n points. Each of the L's are 1, and in that case, it's just so sorry. These have to be different. I didn't say. These are different points. You choose n different points, and then it's, of course, the stratum of n different points in the plane. And so this is what we started with. So this is the sort of compactification we have.
So now you write the Hilbert scheme as some huge disjoint union because this is topology.
Yeah. So I wrote it this way, but in fact, the idea is that you see here, I can just choose these. Well, I wrote that this way, but maybe I could have written it separately. So I fixed these L's, fixed the partition, and then I just changed the points. See, so I could maybe, I could slightly write it slightly better. I just didn't have enough space. So, but okay, so you write it this way, and then you just say here that it's say union for, so if I write it this way, P1, Pk, so these are different points in A2, and then I write this product. Then this part is just fibered over k different points you see, so yes, each of these products is a separate piece, but I'm taking a union at the journey over k different points. So you can think of this as just, this is a smooth space, k different points on the plane, and this is fibered over that with sort of trivial fibers. I mean, they're just move. So each of these pieces, as I take the union, so each of these pieces, so and after I fix these, each of these pieces is a topological space, and there is only finitely many of them now. And that's what I mean. Of course, it's still disjoint union, so it's, in fact, it's in that vein that we did at the very, very first thing, that you represent things at the union of affine spaces as disjoint union of different dimensional affine spaces. It's that sort of what I call motivic or additive decomposition. But this gives you a picture of what the thing looks like. That's what I wanted that you see, that basically the Hilbert scheme of endpoints is just consists of a finitely many pieces parameterized by partitions, and these are the pieces. And so what you need to understand, of course, each of these pieces, because it's product of these. And this is what I wanted to explain next, of what approximate to what this looks like, okay? So that we have an idea of what it is. But so once you understand what this is, then in a sense it's easy. It's sort of, you just put it together. Well, still the topology actually is not clear how you put it together, but at least you have you can list all the points of Hilbert n using this. Okay, so let's discuss this for a second. This is kind of amusing. This is at the beginning, it's even kind of hard to imagine what it looks like. So what about this space now? So what about Hilb and 0? And so the idea is the following. So I'll give you the theorem of Briançon. We certainly don't need to know the proof of this. So theorem of Briançon and it says the following is that Hilb is an irreducible n-1 dimensional variety. Okay. So of course this is consistent with this because n was 2 and p1 irreducible n-1 dimensional variety. The thing that is just slightly surprising is the following fact, is that if you take, so now it looks like this really beautiful picture. So, yes, I missed one thing here that I wanted to say, sorry. This is true, but so here I wanted to say something. Sorry. Would be a little clearer, okay. So, sorry, just we add this thing into this little space, is that what this also tells us, if you look at this, is that or even there already I could have said this, that now we can define what's called the Hilbert-Chow morphism. So that's one more thing I wanted to define, is the Hilbert-Chow morphism. And this is just the following simple thing, is that you take an ideal and now you define an element, if you like, of the Chau group, well, not really, but an element of the symmetric product of the sum of multiplicity P of I for all P again. So, yeah, I forgot. I should have said it here actually. So this is, once you have this picture, then to each ideal you can have you can take a formal sum of the points in the support. If I can add this, that's so important, with the corresponding multiplicity of the ideal there. So, like in this case, for example, the idea I was saying here would be just this point, but this point plus twice this point. Okay, so and this, and this is sort of course, this maps into the formal sums of n points. The sum of these coefficients is always n. You see, so it's a formal set of n points, but they could be a repetition of the same point. Okay, so what this says is that this actually maps the Hilbert scheme of n points to the symmetric product. To the symmetric product of A2. By symmetric product, I precisely mean just the formal sum, well, the sum of, well, there's various ways of, obviously this is a space, you can look at it as the product divided by the symmetric group, or just formal sum of, okay. So you have this space, and then if you think about this picture now, then the Hilbert scheme maps. So this is this symmetric product. So what you see here in the bottom is kind of this singular space. So A2 is very singular. And then the Hilbert scheme is some kind of beautiful resolution of these singularities. If you take this n times the origin here, so the origin is this point 0, 0, right? In the symmetric points, you just take n tuples of things. So then above this, you have this punctual Hilbert scheme here. Okay, so this is the picture. And so then there is this map, which is the Hilbert-Chow morphism. Okay, and so this thing here is n-1 dimensional. The thing that's a little bit strange is that this is singular if n is greater than 2. N is strictly greater than 2. So even though, okay, so this bottom thing is singular, this upper thing is beautiful and smooth, but still if you take a fiber here, then this will be still singular. So this is a little bit peculiar. Okay. And so what else I wanted to say? I just wanted to say, give this general picture of this thing. Yes. So I wanted to explain this n-1. Okay. I want to explain a little bit this n-1. This is also something that you don't really need, but so curvilinear Hilbert schemes, subschemes. So I want to explain this n-1 dimensionality and just construct some elements here. So this is really just an extension of what you saw here. So you remember for Hilb 2, what you just had is that you just had a tangent vector basically in some direction, right? And so that was your scheme. And so you just need to generalize this. So the idea is that you construct sort of what's called like a jet of a curve, but you can simply think of it as you just construct a curve. For us, you can think of it as a finite, well, you'll see in a second. So just with finitely many derivatives. So I'm going to construct points in the Hilbert scheme in the following way. So this is the construction. Let V1, V2, Vn to be just vector. But we think of this now not quite in affine space. We think of it maybe as in, well, I'll call it A2, but we think of it as vectors, okay? And this is going to be the velocity vectors of the derivatives of an actual honest curve, okay? So let's consider now gamma. And this is a parametrized curve, and it looks like this. So this is just t to the I, sorry, it's n-1. A t to the I times Vn-1. Oh, sorry, Vi. I goes. It's tough this semester, no? I mean, and you have 5 of these courses, right? Okay. So, okay, so we just look, you see what's happening here. I just look at a curve. It's parametrized by t, and its derivatives are these vi's. Okay, and now we will be considering it starts at 0, this curve. Okay, and I will be just considering functions f. So to this gamma, I can associate an ideal I gamma, which is just all the functions which vanish on this curve up to degree n-1. So these all functions in R, or it's a little better to think of these over as holomorphic functions. You have power series, it's a little easier, but anyway, you can think of it this way as well. F in R such that F, well, you just make the substitution now. Gamma is equal to 0 up to degree n-1. Okay, so what I mean, so what does this mean? I mean, so you have a polynomial, and here you have some. So if you like, so you can also write this differently, of course. I mean, you can write Vi as A alpha I and alpha Ix plus beta Iy. So then you can write this way. This is just sum of alpha I t to the I x plus beta I t to the I y. Right? These are just the alpha I beta are just the components of Vi. And so then the idea is that you just make a substitution for x, a substitution for x, which is this coefficient, and for y, which is this coefficient. So right, so you have the curve is a map from, so you think of this gamma as a map from A to A2. And then the functions in the ring are, of course, the function is, of course, a map from A2 to the numbers. And then you just compose them, okay? And then you just want to know, you create an ideal, which is 0 up to degree n-1. So that means you make this substitution of these two things, and then what your requirement is that there would be no terms up until t to the n-1 in it, okay? So when you do the composition, no terms with t to the L L less than equal to n minus 1 in the composition here. This is this condition. Okay, so actually it's sort of like you want to say that the function f vanishes on this curve. That's what you want to say. But you don't say that. You just say that it vanishes up to degree n, or n minus 1. Okay? This is a completely explicit calculation. You can do it here. Okay, and so this way you define an ideal. This ideal is supported. So now I gamma is supported in at the origin. And this is going to be here. So I constructed for you a bunch of, so for each sequence of these vectors, I constructed you a bunch of ideals there. Okay? So what is the dimension of this thing that I constructed? That's the question now. Okay, so I mean, if you can, pardon? So you construct the, I'll just count parameters. So the dimension of the space of curvilinear, this thing is called a curvilinear subspace, curvilinear subschemes is equal to, well, I mean, if you do it naively, you have 2n minus 1. You have 2n minus 1 vectors with 2 parameters, right? You need 2. So it's 2n minus 1. Well, that seems a little excessive because I just said in that theorem that it's n minus 1. So what happened here? So why? So of course, obviously, the point is that different curves could give you the same ideal. And so how does that happen? And that's very amusing. So what you need to do is the following. So suppose that you do the reparametrizations. And the reparametrizations is the following. So suppose you have like t. And now this is equal to sum of omega I. These are just numbers now. Times t to the I goes from 1 to n minus 1. So, oh, sorry, that's not t. That's an s. Okay? So you think of this as just a map from A to A, or from numbers to numbers. Right? So you just map S, you take a number S here, the omega i's are some fixed numbers, you make S, and then you get a T. Now you can make this substitution, so clearly you think of this as some map delta. So then it's easy to see that the ideal corresponding to gamma and the ideal corresponding to I gamma composed with delta is actually the same. Sorry, that was a different delta. So I make this substitution. And again, I mean, I'm not explaining this in detail, but when you make the substitution in the curve, then you always throw away the terms that are degree higher than m. You will have such degrees because you have here degrees n minus 1. When you substitute into t to the n minus 1, you'll have degrees 2n minus 1. You throw away the terms which have, so simply ignore everything. You throw away the terms which are above degree n minus 1. So in fact, you're working in the ring t to the, this quotient ring t to the n equals 0. But I just decided to make it simpler, say this way, okay? And so now, if you count ideas, you count what is the dimension of the space of deparametrizations of the group. Actually, these form a group. It's easy to see. Group of reparametrizations. Well, it's written here. You have n minus 1 number, so it is equal to n minus 1. Because you have n minus 1 omegas there, right? Just these are the n minus 1 omega i's. Right? And so this gives you the count. The count is then the curvilinear part is equal to twice n minus 1. This is the 2n minus 1 two-component vectors minus this n minus 1, the redundancy, and this is equal to n minus 1. Okay? And this is this n minus 1 here. It's the, so as I said, it's an irreducible n minus 1 dimensional variety. It has a beautiful smooth part, which is just given by this quotient, which is these curvilinear parts. And then there are some other parts that are of course not curvilinear, but they are of higher codimension. So this is the generic part. The generic is curvilinear. So just our examples. So for n equals 2, as you saw, so then of course everything is curvilinear. So Hilb 2, 0 is the same as the curvilinear part. I didn't introduce a notation for the curvilinear part, but obviously a subset. So I call curvilinear, of course, an element, a subset of the Hilbert scheme, Hilb 0, which arises in this fashion, right? And then for n equals 3, it's amusing. So L3. So this is equal to the curvilinear part. And then there is a single element that's not curvilinear, and that's this plus a single point. So, and this is the ideal generated by, well, m squared. So that's just the ideal generated by x squared, xy, and y squared. So for 3, n equals 3, everything is curvilinear like this. It comes from curves plus something that's splashed out like that. And then later it becomes much more complicated. Classically, this has been studied a lot. They did it until degree whatever 6. Everything is classified, and then nobody knows. So this is not so easy. So yeah. So now, so this is just, I wanted to give you a general picture of this space, of what the thing looks like, okay? And so now we are actually going to, to the part that I would like you to learn. And this is related to localization and calculations. And maybe I'll say one more thing since I had this preliminary part, or the general things, which is the following: is that Hilb can be globalized. Hilb can be globalized. Actually, it follows from what I said at the beginning. Globalized. In the following sense that, well, just for simple, it can be defined for any surface. So Hilb N S can be defined as the same way subschemes of colength 1. So same way subschemes of colength 1, or colength n, what I'm saying. Very tired today. Okay, in where S is any surface, S is a smooth surface. So this can be defined, and this is not so surprising. If you look at the decomposition that I was doing, then of course the decomposition says that it's enough to understand this Hilbert scheme when all the points are at one point, because then the rest in general then is just the union when you take products of those, so that product form that I was saying. If you think of that for any surface, then again it's enough to understand the Hilbert scheme when all the points are considered at one point, and then of course you can think of that as an affine space. So then it's not different from the affine space. Anyway, this is not so crucial. Maybe what is you can actually have a slightly better picture, and that's the only thing I want you to learn or think about is what it is for P2. For P2, it's a little clearer what we are doing because P2 is covered by these affine charts, and then on each affine chart you take the Hilbert scheme, and that will be a subscheme here, right? So you have A2 in P2. So if you have a subscheme in A2, that's also going to be a subscheme in P2, and this way you can glue together the Hilbert scheme of P2 from the Hilbert schemes of A2 in sort of in obvious fashion. And that's what we have in mind. Okay, so defining if we believe we understand what subschemes are, so that I didn't explain much of that this semester, but last semester you learned, of course, what subschemes are. So then by tautology, we defined the Hilbert N of P2, right, this way. Okay. So I will consider that defined in you'll see what you need precisely for that. So for the calculation. The reason I want this is because now we really have an actual problem we can pose, and then I said that has enumerative significance, but we just care about numbers. So for example, I want something projective so that I can calculate Chern numbers. That's why I did this. But so I can ask the following thing. So you still have this Hilbert P2, and you still have this tautological sequence. Well, now I'm not going to put that thing. It's going to be now a projective sequence. In any case, we have this algebra we still have here. So we still have this A. Okay. So A is a rank n bundle. So you have an honest rank n vector bundle over A, and this Hilbert N P2 is a projective smooth variety. So if you put everything together, I said today, then you can plausibly believe in all what I'm writing here. So now you can. So now, since P2 is projective, the colength and subschemes are also going to be projective. It's going to be smooth because locally it's described as the Hilbert scheme of A2, which is smooth, and this bundle A, since it is just the functions on the corresponding subscheme, it's invariantly defined, and so you have this bundle also. Okay. So you have this rank n bundle, a smooth projective variety. Now we can do our thing. So the question is, what are the Chern numbers of A, for example? Okay, so this is still an open problem, actually. So this actually are explicit conjectures and people don't know how to prove about this. So even formulas, so what I will want you to do is just to prove this conjecture So what I want you to do is just to, I show you, we have an explicit algorithm to calculate these numbers. It's just this algorithm becomes very complicated as you go on. But I want to explain this algorithm because that's completely within what we've done. It's not difficult at all. Okay, so I'll do that now after the break. Okay, so this is the plan. So what we need to know for that. So mainly we will just work not on P2 but on A2, and then it's easy to extend what I'm saying to P2. So let's just look at A2 for now to understand the data. So what we need to know, so localization data of this sequence on A2. So that is what we are discussing now. So first of all, localization, you need a group, right? So let's maybe now I'll just, for a simpler notation, I'll say that A2, the coordinates on A2, this will be just x1. There's obviously a T, so a C star squared, which as usual I'll denote by T, a torus action acting on A2. And this is just the obvious thing. So you have T1, T2 acting on a pair x1, x2 is just going to be T1, x1, T2, x2. Okay. So when I am saying a weight of this torus, so a weight, as usual, of T, it's just an element lambda 1, lambda 2, let's call it that, in z squared. So it's just two integers, and each the set of weights is just a group homomorphism from T to C star. So if you have some, this is say lambda. Roughly, well, not roughly, just in somewhat more efficient notation, I'll call this T, this element. Then I can say that the weight lambda gives rise, this is just notation, lambda gives rise to a homomorphism T, it's a homomorphism T to C star. This is a group homomorphism, and it's given by the following way, that you just go T and goes to T to the lambda. This is a notation, so it's just T1 time to the power lambda 1 multiplied by T2 power lambda 2. So this is our basically our usual setup. I'm just reminding you what this thing looks like. Okay, so one important thing is that now acting on A2, I also act on functions on A2, so I also act on R, right? So this way, a lot of things become representations of T. So in particular, T acts on R, right, which is this polynomial ring in two variables. And if you want to understand the weight structure, then there's a very pleasant way of doing this, which is just we write down all the monomials and R in a table, so it looks like this, right? So right, so here we find just the function 1. Here we find x1, x2. Then we have x1 squared, x2 squared, x1, x2, right, etc., etc. So I write what I'm doing on this diagram. I'm writing down a basis of this polynomial ring, which are all the monomials. Okay, so this we all know. But one thing is worth pointing out is that as this is a representation, as you remember, every representation decomposes as direct sum of one-dimensional representations. So, and in fact, these form a basis of one-dimensional sub-representations of R. So each of this will carry a weight. And so the point is that if I have here some square x1 to the L, x2 to the L, then s2 to the k, say, or maybe, well, let's call it so. I already started, sorry. Lambda 1, x1 to the power lambda 1, x2 to the power lambda 2, then this will, this monomial, when you act on the torus, but it just goes into multiple itself, so it's an invariant monomial carrying a weight. So this carries weight. I think the correct thing to say is that carries weight minus lambda 1 minus lambda 2 because of a convention. Okay. So that's because it's a bit confusing. Yeah, I think it's correct. Because here I'm acting on the plane, and here I'm acting on functions on the plane. So when you act on a function, it becomes the opposite sign. It doesn't matter. It's just a sign issue, which I always confuse, as you know. So, okay. So we have this diagram of this R of these monomials. So now, obviously what we are interested in now is if you remember, so what our yoga is just, we have a space. This is the Hilbert scheme. We have now a torus. So a torus acts on R. So of course, if torus acts on R, yeah, last thing, see? This, of course, induces a torus action on Hilb N. Right, so this is clear because the Hilb N, remember, is a set of ideals in R. It's like the Grassmann. It's a set of subsets. And it's easy to see that this torus section carries an ideal into another ideal. And so this Hilbert is invariant. So if you take an ideal, you rescale it a little bit like using this rescaling, and you get another ideal. Okay? So for the example, you should keep in mind, which you saw, for example, for n equals 2, right? So what is really happening is the following, is that when you have, so here's the origin, here is the plane, right? So if you really have two different points, for example, then, so this is just the origin, it's a hole, and here are the 2 points. Then these 2 points have 2 coordinates, and when you act by T1 and T2, they are just carried, you multiply both coordinates by, say, if they are both 1/2, for example, T1 1/2, T2 1/2, then this is just carried to, so this is 0, this is the origin. This is just carried to here, and this point is carried to here. So the ideal of these 2 points will be carried to the ideal of these 2 points. I mean, that's the action, right? So it's kind of obvious. However, if I look at the situation when you had this ideal contained at the origin, then it looks slightly different. So you remember when it's not 2 points, so this is the case of 2 different points. And then still for n equals 2, but now I'm looking at the case when it's both points are at the origin. You remember, I mean, that's what you did in the homework. It has the following form. Then the ideal to now supported at the origin, so both points are at the origin. So then the generic element, that P1 that I was writing about, that looks like this. The ideal is just like sum alpha x1 plus beta x2, so you have some linear function, and otherwise you have this m squared, this ideal, which all quadratic forms. So you have some, x1 squared, x2 squared, x1, x2. Okay, this is somewhat redundant, but it's clear this way. Okay, so this ideal is a codimension 2 ideal. You have 1 and then one of the linear functions that are missing somehow, right? Okay, and so it's very clear what's happening here now when again, I just want to see how what the action looks like, right? That's what I'm looking. So the action here, for example, is here. Here the action is going to be, well, this was a bit unfortunate that I put it through, but anyway, so here, say T1 is 1 and T2 is 2, then the action is just going to be, this is carried to alpha x1 plus beta, so I guess the weights are the opposite, so I have to divide by 2. And then plus all this stuff remains here that doesn't change. So you see this linear function changes, so actually it's moved, and of course that corresponds to moving the P1, I mean rotating it. Okay? All right. So back to our yoga. So our yoga was that we have a smooth variety and we have a torus acting, and then we had to do the following. And we had this bundle situation, and then we had to find the fixed points, and then at the fixed point we had to find all the weights of the tangent bundle, that's C and T, that's in the Bott residue formula. So I'm trying to put together the data of the Bott residue formula for this setup that I mentioned. So with that bundle A over the Hilbert scheme. So that's what we are trying to do. So far, okay, so I constructed the smooth space. I have the torus action, which is induced by just the acting on the plane. That, of course, also moves points in the plane and moves the ideals in the plane. So that's fine. And then now what we're interested in, what the fixed points are. So the question is, what are Hilbert T, the fixed points, fixed ideals? Okay, and this is actually an easy exercise. The proposition is that fixed ideal, so the fixed ideals are the monomial ideals. Ideals, so they are necessarily supported at the origin. Okay? And so a monomial ideal supported at, ideal generated by monomials. So monomial is something like these things that you see here. These are the monomials, one of these basis elements. Okay? So this is a simple fact because the monomials are the eigenvectors of this torus action, and maybe just one. One word maybe here just in this example. So this is, for example, in general not a monomial ideal because x1 plus x2 is not a monomial. So if beta is 0, this becomes a monomial ideal. And then alpha equals 0, this becomes a monomial ideal because you see it's generated by all monomials if this is not here. Then the combination is not. So that's what we mean by monomial ideal. Which ideals are monomial, of course, depend on the choice of coordinates. So that's not an invariant notion, but in any case, we have fixed the coordinates. In that case, it's meaningful. And how to just to an indication of the proof is that well, actually, you can write down very nicely the generators of any ideal, because basically what you need to do is that the generators quite clearly are, so generators as an R module. So what we do, we take the ideal and then we take all the elements that are generated already by some other elements. So what are they? So obviously if I have some other element and I multiply it by x, then it's generated. Or I can also look at the ideal and multiply by y. These are the elements that are already generated by some other elements of I. And this is the whole of I. And this quotient is exactly the generators. Okay? So for example, let's look in this case. So if you, let's look at an example when you have, say, you and I describe a monomial ideal for you. So the language is the following, is that I look at, this I need to explain a bit better. Anyway, so let's just believe in this, and I'll give you some examples in a second. Anyway, so this is naturally the generators, and this is always finite dimensional. And if I was invariant, so if I is T invariant, then so is this gamma I, these generators. And then you just take the finite dimensional decomposition. This is a finite dimensional vector space. And you just decompose it into some weight vectors, right? So as a torus, gamma I, and here you put some lambda. Well, lambda is some set of weights. And naturally, necessarily, these pure weight subsets of this gamma I will have to be some monomials because the invariant, so this will be spanned, or you can also spanned by images of monomials, because they are by the previous observation of monomials. Because these are precisely the invariant vectors of the torus action. And so the geners are monomials, and that's the definition. Okay? But so I will not require you to know this proof. I just wanted to vaguely explain what the technical trick is actually just that you can show what the generators are via this formula, and then the rest is just a little manipulation with the fact that the monomials are the invariant polynomials, the only invariant polynomials under this torus action. Okay. So, but on the other hand, another proposition, this is almost evident proposition, that in fact the monomial ideals are in one-to-one correspondence with the partitions N1, well, I'll write it already this way, plus, so these are ordered partitions Nk of N, so we'll do ordered partitions, so like this. Okay. And so the correspondence is simply the following, is that you take a partition and you measure it as a column. So for example, let's look, I'll do a proof by example as I usually do. So example, say n equals 6, and let's look at the partition, say, so I'll do two examples. So the partition case 1, say 3, 2, 1, and then case 2 is say 2, 2, 2. Okay, and so for 3 to 1, so here it's 3, so you go have 3 boxes, 2 boxes, and 1 box. You draw this curve. It's important that they are, decreasing, and it's easy. It's obvious then that the ideal, which is the complement of this diagram, so the ideal corresponding to this is equal or spanned linearly, spanned by monomials in the complement. Okay, so this is this case, and so of course, and then you can do another one. So that it would be like this then, 2, 2, 2, 2, and this would be this diagram. And so then it would be the monomials in the complement. And you see the point is that what does it mean an ideal? Why, it has to be an R module, so it has to be invariant under the action of x and y. And the multiplication on the monomials by x, so this is multiplication by, x1, and this is multiplication by x2, right? So this is the action, and so you can see that if you have a staircase thingy like this, then if you had a monomial in an ideal, you multiply by x2, you remain in the complement, and here you remain in the complement. So this is really an ideal. And it's clearly monomial, and so according to this proposition, these are the fixed points. So in fact, for Hilbert n, there are as many fixed points as many they are partitions. And so once we have this, so then we just need our data, Bott residue theorem data for for the tangent bundle. And so maybe first I do the simpler case. So you remember we have this story. A, Hilb, N, and we would like to understand so now there's a discrete, there's a finite set of fixed points here. And at each of these fixed points, we want to understand the weights. So you remember in the Bott residue theorem, we need to understand now I choose a partition, like for each partition, partition n1 plus nk, so I'll just write it this way, of n, we need the weights of the corresponding A. So then maybe I do need to denote this by somehow. So let's denote these partitions by sigma. So sigma is a partition like this. So then I look at A and I look at I sigma. Okay, so for each partition, like 3, 2, 1, I have an ideal which is described here, which is the complement. That's the ideal I sigma. And of course, A I sigma by definition is just the quotient algebra here that comes from that sequence. Remember, I goes to R mod I. And so these weights are easy to describe because, like for example here, so again, proof by example, 3, 2, 1. So what are the weights? Are just the weights of the monomials that you see here. So the weights are the weights of the monomials in the diagram. So by diagram, I mean the marked part. This blue part is a diagram, and this is the complement of the diagram. Okay? So in particular, for example, for 3, 2, 1, you just list, so there's always the weight 0 here. So these, I have to give you 6 weights, and so they are just 0, 0, 0, 1, 1, 0. So these are just, I'm listing the weights of these monomials. This is 1, 0, this is 0, 1, and then there is all the weights of some 2. So 2, 0, 0, 2, and 1, 1. Okay, so these are the 6 weights of this bundle A, the fiber of this bundle A at the fixed point I sigma. Okay, so this is the easier part. And so the last thing I will tell you, the slightly more difficult part, is the following. So I'll just give you the last ingredient, and this is the weights of the tangent bundle. Okay, so you remember, so recall that the tangent bundle at any ideal of the Hilbert scheme is naturally given, this is what you were sort of doing there, is naturally given by Hom as an R module from I to this A. So R mod I. So A is just another name of R mod I. Okay? And so now what we have, so now I have a sigma, so I have this diagram sigma, a partition sigma. There's an ideal I sigma corresponding to it, and I need to understand the weights of this thing. So the problem for now sort of a proposition. So let's, again, sigma n1, nk, just a partition of n. And so then there is a corresponding I sigma monomial ideal. And then I want the weight decomposition of these things. So then the weight decomposition, so the weight, simply the weight of this Hom R I, R mod I, are given by the following list. So what we do is the following. So I have this diagram. Some diagram. And so let's denote, so I have sigma is the partition, and let me now, the set of delta sigma is the diagram. Sigma is going to be all the squares, so the set of squares in the diagram. And I take now one of these delta sigma, so delta sigma has n elements, right? It has, so for example, here, what I'm saying is like 3, 2, 1, these 6 squares here, the 6 monomials are my delta sigma, okay? The answer will be a sum over these things. So then the weights of R are given by, so it's just notation, so I are given by, and so I continue this sentence, given by, and so this is some notation, and the following way. So for each squared in this diagram, so I take the list of the squares, so like take this one, this one, this one, this one, this one. I do the following operation. I go up here. So I go up here, and this is called the arm. This combinatorics really call these things this way, you won't believe it. And this is called the leg, okay? And now, so this is a length. It's the number of squares you have to go until you reach the boundary of the thing, okay? So not counting the thing itself. And if I'm saying it correctly, so it's one, yeah. So this is the arm and the length. So there's 2 functions for each thing. You now have 2 integers, the arm of this squared and the length of this squared. So these are just 2 non-negative integers, which is just the distance until the corresponding things, okay? And so for each of these, you introduce the following 2 weights. So one of them is just L plus 1 and L plus 1, sorry, L plus 1 and A. And the other one is, minus A. And here minus L, of course it's symmetric, and A plus 1. Okay, so of course it's, so now I have to look at the time, so I definitely don't want to go over. Okay, so actually this is the answer. So again, you remember the dimension, here just to recall, of the space is 2n. So there should be 2n, I give it 2n weights. There is n boxes, and for each box I give you 2 weights. That's 2n weights, and these are the 2n weights, okay? And they are constructed this combinatorial way, okay? So I was planning to give you the proof of this, but obviously I'm not going to do that now. But it's a completely elementary combinatorial thing. I just want to make one remark why this is obvious, why is it natural that you would have these weights? Because you remember, you want to have hom I to r mod I. So on the picture, actually, you can see this. You want an R homomorphism, a homomorphism of R modules from I, so that's I is the complement, to R mod I, which is the diagram itself. So you want to get from here to here. And one natural way of doing that is that here, you have, so for example, you have a square here. This is in I. And you have another square here, which is in R mod I. So these boundary squares, you have a kind of a boundary square, if you like, of I and the boundary square of R mod I. Which precisely boundary squares you need to take? Well, then it's a combinatorial problem that's actually very easy to do, but we're not going to do that because I didn't have time to finish this. But anyway, so this homomorphism just simply says that this element of I will go to this element of R mod I. And that naturally gives you a weight. Of course, the I will give you this L delta plus 1 thing. So I'm doing the opposite one. So I delta plus 1. So this that I showed you, this gives you an element from here to an element of here. Okay, so this morphism from R to R mod I is precisely given by this element going to here, and then there's an extension. Of course, I only told you where one element of I goes. You have to tell me where all element of I goes, and it's a combinatorial lemma or a combinatorial argument to say that this particular, if I fix the morphism that this element of I goes to this element of R mod I, can be extended in a unique way to a morphism like this, and there's a one-to-one correspondence between well, this sort of thing and the homomorphism. So it's a purely combinatorial thing, which if you're interested, especially if you're here next year, then I'm going to explain it at the beginning. Okay, and so this is our data, and now we have the complete combinatorial data, and so you can write down a residue theorem. So for example, if you want to know C1 of, so let me just quickly show you how what I mean by this. So if you wanted some Bott residue data, so the Bott residue formula. For this case, then the contribution, so I'm just telling you what the contribution at I sigma, one of these fixed points. So now you know all the weights, so this you remember there was some, so you have the notation I introduced the last time, so you would just have some polynomial phi, you remember, in the weights of this A sigma divided by the product of all the weights that I introduced, so the product over all squares in the diagram. And then you have the product of the two weights. Yeah, so this would be like this. Yeah, so the two weights that I have there. So the weight 1 times weight 2. So one, just a very last thing is to make it a little more similar to what we were doing, it's useful to take a subtorus, so take this subaction when you have, where you just have a map from C star to our torus T, where just the element T goes to T inverse. So that has the effect of collapsing each weight to the difference of these two weights, so you subtract this weight from this one. And then instead of these two-dimensional weights, you just have numbers again, as we had before, and so then those numbers will give you the actual contribution. Okay, so stop now.